Okay, so now I'm going to continue and just briefly show you the quantum mechanical derivation of the singlet correlations. And the thing is that they are just abracadabra. They are some formulas, and they use a formalism, and it's a formalism which works, as we now know very, very well indeed. Okay, so you don't have to understand this, and there's a point of view which says you cannot understand this, you just have to accept it. Right, I start off by defining three operators on the Hilbert space C2. So they are actually can be represented by 2 by 2 matrices, and they're called the Pauli spin matrices. And they are called sigma X, which is the matrix with ones off the diagonal and zeros elsewhere. Then there's the sigma Y, which is the matrix with minus I and I off the diagonal and 0 on the diagonal. And sigma Z, which has got 1 and minus 1 on the diagonal and zeros off the diagonal. And just note, well, these matrices are self-adjoint or emission. They're equal to their transpose and complex conjugate. They have a very nice property that they square to the identity, the 2 by 2 identity. Because they're self-adjoint, they they can be diagonalized and have real. So you can find an orthonormal basis of eigenvectors. Well, that'll be two eigenvectors of each corresponding to eigenvalues, real, which will be real. And because the matrix is square to the identity, their eigenvalues square to +1. So their eigenvalues are plus or minus 1. Well, and I will mention that they do not commute. They anti-commute, in fact. But I'm not going to do any calculations with using that property. Well, I'm not going to do the calculations. I'm just going to write down some things and make some claims. And if you want to do try to go through them yourself sometime. Okay, now I'm going to define another spin matrix, which we're going to call it spin in the direction A, where A is a unit vector. So I'm going to define sigma. First of all, I'm going to define a vector of three matrices, sigma X, sigma Y, and sigma Z. I'm going to let A be a real vector of length 3, of length 1, so a unit vector in R3, and I'm going to define spin in the direction A as A dot sigma. So it's just AX sigma X plus AY sigma Y plus AZ sigma Z, where AX, AY, AZ are three real numbers, and we're using the names of the axes X, Y, and Z instead of the usual 1, 2, 3 to label components. Now, sigma A is clearly also self-adjoint, and not so clearly, but you have to, I've told you that it anti-commutes. If you you can use what I've told you before to quickly find out that it squares to the identity, and therefore it has eigenvalues plus or minus 1. Now, I want some notation for the eigenvectors of some of these matrices, and I'm just going to define one of them. One pair of them, EZ. I'm not going to call it EZ. I'm going to use the bracket notation. Let's just start again. I'm going to define plus Z and minus Z to be normalized eigenvectors of spin in the direction z corresponding to the eigenvalues plus or minus 1. Well, and of course you can very rapidly see what they are. They're the vectors 1, 0 and 0, 1. Well, actually I could multiply either of those vectors by a complex number of absolute value 1, and it would still be a normalized eigenvector of sigma z. But okay, this is a possible choice of them. It actually doesn't matter which choice you make, but once you've made a choice, you've made it. Now I'm going to define a vector of length 1 in the Hilbert space C2 tensor C2. So those were elements of C2, and now I'm going to define psi, and it's a big thing because it's actually in C4, and it's 1 over square root of 2. That's to normalize it to have length 1, and then it's plus z minus z minus z plus z. Okay, I was being a bit short in my notation there. Let's put the tensor product in there, and let's put it in there. Okay, that's in C2 tensor product C2, which of course is isomorphic to C4. That's a vector, and this is called the singlet state, or really the state vector corresponding to the singlet state, and it's a state of a system consisting of 2 particles, and each of those particles can have a spin, or each of those particles' spin can be measured. And how do we do that, or how do we write down, what's the formalism for that? We define sigma A tensor identity, 2 by 2 identity. This is called, this is the spin in direction A of particle 1, or subsystem 1. There are 2 systems coupled together, and so of course identity tensor product sigma B is the spin in direction B of particle 2, or system 2, and sigma A tensor sigma B is actually the product, well, it's actually the product of those previous 2 spin operators. So it's the product of spins in directions dot dot dot. Now, all of those 4x4 matrices or operators are all self-adjoint, and they square to the identity in C4. So their squares have eigenvalues plus 1, so their eigenvalues are plus or minus 1. Now the last thing I need to tell you is how quantum mechanics tells us is the expectation values of results of measurement of each of those 3 observables. So that we compute them by calculating the following thing. We take psi, and this is the bra psi, which is this vector which I defined before. but transposed in complex conjugate. So now it's a row vector. Then we multiply it, matrix multiply it to the vector sigma A cross identity. And then we put on the other ends the ket, so-called ket psi, so that's a column vector of length 4. We just calculate that, and I've told you enough to calculate it. When you calculate it and you find 0. Similarly, of course, psi identity tensor sigma B, psi equals 0. So those are the mean values of the results of measuring either spin. And what is the mean value of the product of the results of measuring both spins? It's psi sigma A tensor sigma B psi, and it turns out to be minus the cosine. Sorry, not minus the cosine, because I haven't told you any angles. Let's erase that. Minus A dot B, which is of course minus the cosine of the angle between A and B. Okay, so this actually allows measurements of spin in all directions in space, but in our story we are just talking about directions in an equatorial plane. No problem. That's enough for that moment.